Hello, my name is Kevin. I'm from the University of Washington, and today I'm going to describe how to get fast estimates for tail latencies in big data center networks. My advisor Tom and I had the pleasure of exploring this topic with Prateesh Goyal from Microsoft Research and Mohammad Alizadeh from MIT. Okay, let's go. Imagine that you are tasked with operating a large data center network. Okay, that means billions of messages marshaled and mobilized on behalf of millions of users across hundreds of thousands of machines. Okay, queues are building up here, they're dissipating, they're building up over there, and one thing you know is that your users are going to start to peel off one by one the minute they start to encounter unexpected delays. So it is imperative that the users of your network see reliable performance come what may. Therefore, staying on top of tail latency is crucial. To do that, we'd like to ask questions like this. Okay, if the workload changes, do you need to plan for extra capacity? What about if links fail? Or if you want to tweak some aspect of a congestion control algorithm? We have to plan for operational contingencies if you want networks to deliver robust and reliable performance. We need to keep tail latencies in check. Okay, so goal. Let's estimate the tail of flow completion times quickly and accurately, where a flow is just something like an RPC, and we'd like to be able to do this for many topologies and many workloads. So if I want to estimate something like this today, what do I do? Who do I ask? Well, one thing we could try is to ask NS3. Okay, NS3 is a discrete event simulator. It contains a detailed model of how networks work. You put in a workload and a network configuration, you set it running, and out comes pretty much whatever data you want. Okay, but there is a hang-up, one that's probably tested the resolve of many of the grad students in this room, which is how long do we think it takes to simulate 5 seconds of simulated time on just a modestly sized network of 6,000 hosts? Well, we tried, and the answer is 11 hours on a recent desktop CPU. Okay, why? NS3 is a very useful tool. Okay, it models transport protocols, things like ACK delivery and compression, all the way down to various elements of the physical layer. And data center networks are very complex. They're highly interconnected. Every decision made at every switch affects every flow traversing not only that switch, but also flows at downstream switches, and with congestion control, even future flow behavior. And NS3 captures these details beautifully, but here's the deal. Because of the high fidelity, it can answer a lot of questions, even at the level of individual flows. You want to know how a particular flow is going to respond at a particular time to a particular situation. NS3 can answer that. That's a wonderful thing. But in exchange, you got to wait a long time. However, we want to ask questions about aggregate performance, tail slowdowns, distributions. Well, using NS3 for this is a bit like if we wanted to plant a flower, but all we had was a bulldozer. It's cumbersome, it's a little messy, and more time-consuming than using a more specialized tool like a trowel. So the question is, can we do something more approximate? It turns out we can. As we'll show, we can get to within 10% accuracy, up to 500 times faster than NS3 on a single machine for the 11-hour configuration I just mentioned. Okay, the speed up does not come for free. We do lose some accuracy to approximation, but the central theme is to seed little bits of accuracy for big returns in simulation time. So now I'm going to tell you how to take that estimate from 11 hours to 80 seconds. Here's an idea. If we could somehow consider the effect of each link independently, then large simulations would become almost embarrassingly parallel. Say it a different way. Since we're interested in aggregates, distributionally, how much delay does the congestion at each link add to flow's completion times? Where delay is just how much a flow was slowed down by congestion at a particular link. So consider a flow traversing a path. We think of the congestion at each link along the path as contributing some amount of delay, where each delay is drawn from a distribution we get from an independent simulation. Then to get an end-to-end distribution, we combine the delays. So a hypothesis. Let's model the frequency and magnitude of local congestion events at each link. We'll try a very simple case. Consider a flow that's just a single packet. Okay? What's going to happen to it? It's going to visit the first hop, where it might encounter some delay. It's going to visit the second hop, where it might encounter some delay, and so on. And what might the delay depend on? Well, let's look at a link in isolation as its own bottleneck. The delay, or for a short flow, queuing, encountered by our heroic little packet depends on, first and foremost, the other flows that traverse that link. Not only their sizes, but also how bursty they are. In addition, as another first-order determiner of performance, we should probably model the action of congestion control on the long flows. And that should get us pretty close. So for each link, we run a simulation with these features: bottleneck, workload, congestion control. Out comes a distribution of delay. And then we combine them with some function. That's your end-to-end distribution. For simplicity, we'll just convolve the distributions in an operation that's essentially like addition. Okay, now an underlying supposition of this strategy is when our little flow meets local congestion, that congestion actually contributes to end-to-end delay. Because what do? Look at the first link, this congestion happens, add it. Look at the next link, this congestion happens, add it. For our short flow, this approximation might get us pretty close. Okay, but what about a long one? It's a bit harder, the story's not the same. A long flow doesn't have this one-by-one property. It resides in multiple queues at the same time. So let's say we have a single long flow and it's got a chunk of packets streaming through congested links. What's the total delay? Well, it will encounter local congestion at the first and third hops, that's true, but it's bottlenecked at the second hop. So our method would estimate 200 when the answer is closer to 100. And how bad could it be? Well, with n hops, we could be off by as much as a factor of n, which is kind of a bummer. Okay, but it's not all catastrophes. In many instances, this behavior might be okay. Let me explain. A very long flow will likely encounter multiple big congestion events in its lifetime. Sure, it's true. But we might expect these congestion events to occur in different places and at different times. So let's look at 3 different chunks of a long flow, not necessarily contiguous. Suppose for chunk I, the local link congestion predicts delays that look like this. There's one big bottleneck. Our method will estimate a delay of 105 when the actual delay is 100. And sometime later for chunk J, there's another bottleneck somewhere else, and we overestimate the delay a little. And same thing happens for chunk K. Notice that all 3 big delays from before still occur, but now they occur at different times. And as a consequence, across all 3 chunks, we're only off by about 8%. And so what do we learn from something like this? Well, this approximation tends to overcount delay. If big congestion events happen at multiple hops at the same time, it could overcount by a factor of the number of hops. But if they happen at largely distinct times, we can get pretty close. Here's another issue it helps us with. Okay? Many of you are probably thinking, wait, Kevin just said, for each link, simulate the flows that pass through it. But couldn't those arrivals have also been smoothed by upstream congestion? Very true. But again, if the big congestion events at different hops happen at largely different times, that helps us, and this problem begins to attenuate. As an aside, one thing I want to mention is that our problem of sometimes we should sum the delays, sometimes it's a max, kind of suggests we may be able to do something more sophisticated with this combining rule that takes into account when the local congestion events are happening. We don't incorporate this yet, but it is a future consideration. But for now, we'll say that if indeed data center networks are engineered for high performance, and congestion controllers are pretty reactive and good at clearing huge queues, then our estimates should still be quite close because congestion will pop up in different places and clear without persisting throughout the network for long periods of time. So we implement this technique in a prototype we call Parsimon, which is a fast counterfactual simulator for data center tail latencies. You give it a sequence of flows, a topology, a set of routes, and out comes FCT, slowdown distributions, where slowdown is just this size invariant metric that's like measured FCT divided by the ideal FCT on an unloaded network. Okay, it operates in several steps listed here. The first is to decompose the network in the way I previously described. Each link is simulated independently with only the flows that traverse it, and we model things like congestion control. Earlier, we said what the model for a link-level simulation looks like, but how do we instantiate one? Well, for each link and in each direction, we actually generate a separate topology to isolate the congestion on that link. For speed and memory efficiency, we want these to be small. So we're going to do a little bit of reduction here, but for accuracy, we got to be careful. We need to preserve certain properties of the network. So let's try to isolate the effect of the link shown here. It's in the middle of the network, so flows that traverse it have multiple sources and destinations, so we'll situate it between two switches. Now for the workload that traverses this link, it makes a difference whether it comes from one source or 1,000 sources. If one, it's constrained by one input link. If 1,000, then a lot of data can be dumped into the bottleneck at once. So we'll just go ahead and preserve those exactly. But we'll connect them directly and cut out the extra hops to avoid these topologies getting too big, because there could be a lot of them. But that's still not enough. Remember, we're also modeling congestion control. And one important property that affects the speed of convergence of congestion control algorithms is it takes a whole round trip for signals to be collected along the path and for feedback to be echoed from receivers back to the senders. So we cut out extra hops, but we do have to preserve the round trip times. Here I'm assuming that all the links in the original topology have a propagation delay of 1, and on the right they're annotated. And remember, we're trying to isolate just the red link, so we don't want any other links to bottleneck performance. So as a precaution, we up the bandwidth of the last hop links. The first hop links, we leave them as is, because as before, we don't want too much data dumped into the bottleneck at once. So that's it for this case. There are 2 others in the paper constructed with similar reasoning. So now we have a bag of link simulations that are all independent from each other. Then we look, and we see that some other optimizations fall out pretty naturally. For instance, we know that big data center networks have a lot of symmetry due to, for example, workloads or ECMP. Uplinks in the same ECMP group probably have similar workloads. So we can exploit this symmetry to cluster and prune redundant simulations. And the speed that you get from this, it could be pretty good, but it depends on the topology and the workload. Okay. Once the link level simulations are done, we have a distribution, an empirical distribution of delays per link. How do we combine them? Right now, we just convolve them Monte Carlo style. But I'll add an extra wrinkle. We want accurate estimates across different flow sizes, too. You might want to know, how do short flows behave? How do long flows behave? So for each link, we actually bucket the empirical distributions by flow size. And for a little extra size and variance within each bucket, we normalize delays by the flow size in packets. Okay? So to make a point prediction for a flow with p packets, we sample from the appropriate distribution from each link along the path and combine them like so. End-to-end distributions just come from a bunch of these point predictions. Now let's see if it can work. Here's some workload data extracted from a 2015 analysis of Meta's data center workloads. There's 3 rack-to-rack traffic matrices I'm showing here, where brighter colors indicate that there's more frequent communication in the traffic matrix. The matrix A is largely inter-rack traffic. Matrix C, the communication is mostly rack local, and matrix B is a mix. And the flow size distributions are also taken from the paper. Those are shown on the right. So first thing, let's pick a workload. We'll choose matrix B, since it's a mix. The web server flow size distribution will make the flows bursty, make the topology oversubscribed, and we'll use some moderate utilization. We'll run the workload on NS3 and Parsimon on a large network with 6,000 hosts, and we'll compare the predictions. Here's what we get. I'm showing you a CDF of flow completion time slowdown, binned by flow size, and zoomed into the tail. We see that across the whole tail, and not just a particular percentile, Parsimon's estimates are pretty tight. As we suspect, they overestimate a little by a few percentage points, but they're pretty close, even for long flows, because congestion is happening due to the burstiness of the workload, which comes and goes in different spots, instead of some long-term mismatch between capacity and demand. And the network decomposition allows us not only to parallelize, but also to cluster and prune and do some other optimizations. So all told, instead of waiting for hours and days, we can get it done in seconds or minutes. Also, we want to know, in what circumstances is accuracy bad? So we perform a sensitivity analysis sweeping over traffic matrix, flow size distribution, burstiness, oversubscription, and load with 200 different configurations. And we find that the most important determiner of error is persistent load, which based on what we learned before is not that surprising since high load results in more persistent congestion. But at low to moderate load, persistent loads of about 50 to 60%, Parsimon is within 10% of NS3 about 96% of the time. So the analysis of the other parameters, oversubscription, flow size distribution, matrix, can be found in the paper. In general, it takes a combination of factors in this setup to produce high error, and the paper will list all of the worst cases and tell you what they are. So to finish up, we provide some data to suggest that in many conditions, simulations for tail latency can be fast and accurate. We propose a specific set of techniques to compute tail latency in parallel fashion. Okay, not the only, but it demonstrates that approximate simulation could be a useful tool in an operator's toolkit, and this is a step in that direction. Finally, we implement these techniques in a prototype called Parsimon, and we get tail latency estimates orders of magnitude faster within 10% accuracy. The GitHub link is on the slide. That's all I've got. Thank you very much for your attention.